There are monsters out there, ancient, patient, and invisible. For centuries, astronomers have swept the skies, mapping stars, cataloging galaxies, and searching for answers. But hidden behind the familiar constellations and the calm glow of nearby galaxies lies something far more dangerous. These are not creatures of myth or folklore, but cosmic engines of unimaginable power, silent predators lurking in the dark. You cannot see them, even on the clearest night. They do not shine like stars, nor shimmer like nebulae. They wait, motionless, until they awaken. At first, they revealed themselves only as distant, dim pricks of radio light, barely noticeable, easy to dismiss. But those faint signals pointed towards something that defied belief. Objects so bright they could outshine 1,000 galaxies, yet so small they could fit inside our solar system. When they feed, they tear entire stars apart, releasing torrents of energy across millions of light years. These cosmic beasts are known as quasars, and to understand what powers them, we must follow a trail through the most extreme corners of modern physics, into the hearts of galaxies and the shadowed edge of reality itself. The 20th century opened a new window to the universe. For the first time, we began to listen, not just look. In the early 1930s, a pioneering engineer named Carl Jansky was tasked with tracking down sources of static that interfered with transatlantic radio communications. What he found was entirely unexpected. Buried in the background noise was a strange, persistent signal, coming not from Earth, but from deep space. It was the first confirmed detection of radio waves from beyond our planet. At first, astronomers were skeptical. The sky had always been mapped in visible light. Telescopes captured what our eyes could see: stars, planets, galaxies. But radio waves revealed something else entirely. When engineers and scientists began building larger, more sensitive radio antennas, they found the sky alive with whispers. Jupiter spoke. The sun crackled. The Crab Nebula hummed. But beyond these familiar sources, there were others, faint, distant, and utterly mysterious. These enigmatic points scattered across the sky. They did not move like planets. They did not shine like stars. They were invisible in optical light, completely absent from the photographic plates of the most powerful telescopes. And yet, in radio frequencies, they blazed. Each one appeared as a pinprick of energy, narrow and sharp, emitting across a broad spectrum of wavelengths. They came from every direction, within the band of the Milky Way, and far beyond it. These enigmatic points scattered across the sky. They did not move like planets. They did not shine like stars. They were invisible in optical light, completely absent from the photographic plates of the most powerful telescopes. And yet, in radio frequencies, they blazed. Each one appeared as a pinprick of energy, narrow and sharp, emitting across a broad spectrum of wavelengths. They came from every direction, within the band of the Milky Way, and far beyond it. Some astronomers refused to believe it. They argued the signals must be artifacts of instrumentation or strange stars hidden by interstellar dust. The idea that such power could come from compact points in space was deeply uncomfortable. Others pushed forward, refining their techniques, sharpening their maps. In the 1950s and early 60s, the field of radio astronomy matured. Interferometry allowed astronomers to triangulate precise positions. The invisible began to take form. One of the turning points came with an object known as 3C273. It was a strong radio source, but unlike the others, it underwent occultations, moments when the moon passed in front of it. By measuring the timing of these eclipses, astronomers Cyril Hazard and John Bolton were able to pinpoint its exact position. Optical telescopes could now be aimed with accuracy, and what they found was astonishing. A faint, bluish object, star-like in appearance, but unlike any star ever observed. The astronomer Martin Schmidt studied its spectrum and saw the telltale lines, fingerprints of known elements. But something was off. These spectral lines were shifted, dramatically, toward the red end of the spectrum. Not just a little, almost 16%. The only explanation was motion. Either the object was speeding away at an extraordinary velocity, or the light itself had been stretched by the expansion of space. Schmidt realized what he was looking at. The object was billions of light years away. This was not merely a scientific footnote. It shattered assumptions about the size and age of the universe. Until then, most astronomers believed the cosmos was only a few billion light years across. Now, here was a single point-like object, sitting far beyond that limit, radiating energy as bright as a galaxy, if not more. It forced the scientific community to confront a profound truth. The universe was far larger, stranger, and more powerful than we had dared imagine. Other discoveries followed. Radio maps of the sky revealed dozens, then hundreds, of these curious sources. Some bright and sharp, others quiet but consistent. Many were completely absent in visible or infrared images. It was as if the cosmos was hiding an entire population of beings, visible only in wavelengths our eyes could never detect. The mystery deepened. What could shine so brightly and yet remain so small, so compact, so elusive? In time, a pattern emerged. These strange radio objects were not scattered randomly. Many coincided with distant galaxies. Others appeared at the centers of large, well-formed structures. Some even showed signs of variability, brightening and dimming over months, sometimes weeks. That variability was key. It suggested that the sources were not large. In fact, they had to be quite small. For light to change within such short timescales, the entire object must be smaller than a light year in diameter. And so, a paradox formed. Astronomers were faced with objects that were at once impossibly bright and impossibly small. They glowed more powerfully than entire galaxies, fit into a region no larger than our solar system. This was not how stars behaved. It was not how galaxies behaved. Whatever these things were, they did not fit within the known categories of astrophysical objects. A new name was needed, a name to capture their confusion, their brilliance, and their unknown nature. They were called quasi-stellar radio sources. Quasi because they looked like stars, stellar because they appeared point-like, and radio sources because that was how we had first seen them. But this name was too long, too awkward. In the end, it was shortened. These objects became known as quasars, and with that name came a flood of questions, each more troubling than the last. What were they? How could they exist? And what in the universe could possibly be powerful enough to bring them to life? The discovery of quasars changed the story of the universe. It forced astronomers to rethink what they knew, to question their assumptions, and to accept that the cosmos held far stranger creatures than stars and planets. It was the beginning of a new era in astronomy, an era where light alone could not tell the whole story, where the universe whispered in wavelengths we had only just begun to understand. The turning point came with one quiet radio signal, one subtle flicker in the sky, an object named 3C273. Catalogued among other mysterious radio sources, it was brighter than most, more stable, and more intriguing. It appeared point-like, just like a distant star, but in radio frequencies, it shone with uncommon intensity. Its signal was precise, powerful, and strangely consistent. Astronomers had no idea what it was, but the moon would soon reveal its secret. In the early 1960s, astronomers Cyril Hazard and John Bolton noticed something peculiar. As the moon passed in front of 3C273, its radio signal briefly vanished. This event, called an occultation, offered a rare opportunity. By timing exactly when the signal was blocked and restored, they could determine its precise location in the sky. It was the celestial equivalent of triangulating a distant whisper in a vast cathedral. For the first time, a match could be made between a radio source and a visible object. Optical telescopes were turned toward the coordinates. What they found was unassuming. A faint, bluish dot among the stars, barely distinguishable from a distant stellar object. It did not stand out in any obvious way. It looked like a star. But astronomers had learned to look deeper. And so, Martin Schmidt, a Dutch-American astronomer, aimed a spectroscope at the point of light, hoping to find the chemical signature, the spectral fingerprint, of a known element. What he found defied explanation. The spectrum did contain familiar patterns, hydrogen, helium, and other cosmic ingredients. But the lines were not where they should have been. They were stretched, displaced toward the red end of the spectrum, an effect known as redshift, and not just a mild shift. The spectral lines were offset by nearly 16%. That was no accident. The object was receding at a tremendous velocity, or space itself was expanding between us and it. Either way, it meant one thing. This star was no star at all. It was unimaginably distant. The redshift placed 3C273 at over 3 billion light-years from Earth. That distance was shocking. At the time, most astronomers believed the universe was only a few billion light-years across in total. And yet, here was a single point of light, sitting farther than anything ever recorded, radiating as much energy as an entire galaxy. It was a contradiction wrapped in photons. If it were truly that far, it must be unimaginably bright. It outshone everything else in its region of space, despite its compact appearance. The discovery made headlines. In 1966, Time magazine featured Martin Schmidt on its cover, calling his observation one of the most significant in modern astronomy. The article compared him to Galileo, the man who once turned a telescope to the moon and revealed its scars. Schmidt, too, had shown the world something hidden in plain sight, something that changed the scale of the cosmos forever. The quiet point of light, once mistaken for a star, was now the brightest known object in the universe. But there was more. As astronomers dug through decades of archival photographic plates, they found something odd. 3C27. 3 had been captured before, many times by many eyes. It had been observed by generations of astronomers who simply did not realize its significance. And even more curious, its brightness had varied. From year to year, its luminosity fluctuated. It was not a static object. It flickered. It pulsed. That meant it was not only powerful, but small. Very small. If an object changes brightness over short timescales, months, weeks, even days, it must be compact. Light cannot travel faster than the universal speed limit, so any internal fluctuation must be contained within a volume small enough for the signal to propagate. 3C27. 3 had changed in brightness in less than a year. That meant the source had to be smaller than a light year across. Yet it was producing more energy than an entire galaxy. Something extraordinary was happening. Armed with the techniques used to pinpoint 3C273, astronomers began to hunt. They matched more radio sources to faint optical objects. Again and again, they found the same story. Strange spectral lines, extreme redshifts, staggering luminosity, and compact size. A new category of object had been uncovered. The term quasi-stellar radio source entered the scientific vocabulary. It was descriptive but clumsy. Eventually, the name was shortened to something more elegant: quasar. Quasars were now a reality, no longer theoretical curiosities or radio ghosts. They were measurable, trackable, and undeniably real. But their discovery posed more questions than answers. How could such small regions of space emit so much energy? What engine powered them? Were they all at the centers of galaxies? And if so, why were some galaxies quiet, while others screamed across the void? The astronomy community was now fully awake. The universe had whispered a secret, and it had finally been heard. C27. 3 became a landmark in the sky, a cosmic lighthouse illuminating not just its corner of space, but our understanding of the universe itself. It showed us that what looks like a star may be something far more powerful. That distant light may carry the story of ancient violence and unfathomable energy. It taught us that we had been looking at the cosmos through a narrow keyhole, and that radio waves could widen that view into something profound, even frightening. Today, 3C27. 3 still shines. It is still visible through telescopes, still pouring out radiation across the electromagnetic spectrum. It is no longer alone. Thousands of quasars have joined it, mapped and studied by generations of astronomers. But it was the first to reveal itself, the first to shock the world, the first to tell us that the universe is not just wider than we imagined. It is wilder, stranger, and more powerful than we ever believed. As the number of quasars began to grow, astronomers noticed something deeply unsettling. These objects were not isolated. They were often found at the centers of galaxies, embedded in the very hearts of immense cosmic structures. This pattern was no coincidence. The brightest, most energetic quasars seemed to be emerging from galactic cores, and in some cases, those cores shone brighter than all the stars in the galaxy combined. This raised a profound question. Could there be more than one kind of quasar? Or were they just the most extreme members of a much broader family? Soon, the term quasar was joined by others. Some galactic centers emitted strong radio waves, while others remained quiet in those frequencies but blazed with X-rays or ultraviolet light. A few emitted jets of charged particles, while others glowed with a soft and steady intensity. The diversity was dizzying. It was as if astronomers had stumbled into a cosmic zoo, filled with strange creatures that all looked slightly different, but shared a hidden common ancestry. To make sense of this growing collection, a new category was proposed: active galactic nuclei. An active galactic nucleus, or AGN, referred to any galactic core that emitted more energy than could be explained by its stars alone. This was a quiet revolution in thinking. Until then, galaxies had been viewed as collections of stars, gas, and dust, gravitationally bound and slowly evolving. But now, it was becoming clear that some galaxies had something else at their center. Something alive, something violent, something capable of unleashing power across vast stretches of space. The definition was deliberately broad, allowing astronomers to categorize phenomena that defied easy explanation. Under the AGN umbrella, quasars found a home. So did radio galaxies, Seyfert galaxies, and Blazars. Each had its own unique characteristics, but they all shared a central trait: an active, radiating core unlike anything else in the universe. The challenge now was to understand what made them tick. Why were some galaxies active while others were quiet? What fueled the central engines? And what mechanisms allowed such tremendous energy to escape from a region often no larger than a single solar system? Clues began to emerge. In some cases, astronomers observed galaxies with faint jets of matter streaming away from their cores, jets that stretched across hundreds of thousands of light years. Others had glowing disks of gas spiraling inward toward a central point. The more they looked, the more it became clear. These were not just bright spots. They were engines. Something at the heart of these galaxies was pulling in matter, heating it, compressing it, and hurling it outward in streams of radiation and plasma. The AGN was not a byproduct. It was the core of the galaxy's power. The birth of the AGN concept marked a turning point in astrophysics. It reframed the way we saw galaxies, not as static structures, but as evolving systems with active, dynamic hearts. It offered a unified language for phenomena that once seemed unrelated, and it opened a gateway to deeper questions about the evolution of the cosmos. If AGNs were so common in the distant universe, did that mean all galaxies, including our own, had once been active? Could our quiet Milky Way have once burned like a quasar? And might it do so again? For years, the energy pouring out from active galactic nuclei remained a puzzle. How could such tiny regions, smaller than a solar system, outshine entire galaxies? What engine could release so much radiation for so long across so many wavelengths? The answer, when it finally arrived, was as unsettling as it was elegant. At the heart of every active nucleus, behind the veils of plasma and light, there lurked a singularity, a place where the laws of physics collapse. The most likely culprit was something long theorized, yet still controversial: a black hole. But this was no ordinary black hole, not the kind left behind by a dying star, which weighs a few times the mass of the Sun. These objects were titanic, millions, sometimes billions, of solar masses compacted into a point with no surface, no escape, no second chances. They were supermassive black holes, gravitational monsters capable of bending space, time, and light itself. And they were not just theoretical. Astronomers found one, close to home, hiding in plain sight at the center of our own galaxy. Toward the constellation Sagittarius lies a bright radio source known as Sagittarius A star. It had long been noted as unusual, but as telescopes improved, something remarkable was revealed. Stars near the center of the Milky Way were not drifting casually through space. They were whipping around an invisible point with incredible speed, some moving faster than any known object in the galaxy. Their orbits formed tight ellipses, looping around. Nothing. Whatever was there had to be dark, and immensely heavy. By applying the laws of motion and gravity, astronomers calculated the mass of the unseen object. It was over 4 million times the mass of our Sun, confined to a space smaller than the orbit of Mercury. There was no other explanation left. No cluster of stars could be packed that tightly without tearing itself apart. No object made of matter could remain stable at that density. The conclusion was unavoidable. Sagittarius. A star was a supermassive black hole, our very own. The existence of this beast in our cosmic backyard answered many questions, but raised even more. If our quiet galaxy hosted such an object, then surely other galaxies did too. Perhaps every galaxy. And if these black holes could feed, consuming gas, stars, or dust, they might become active, igniting the violent processes that fuel quasars and active galactic nuclei. The terrifying truth was that quasars were not alien or exceptional. They were simply galaxies, like ours, in a different state of being, awake. In the year 2022, the Event Horizon Telescope gave us a glimpse into the darkness. Using a global array of radio observatories, scientists captured the first image of the region surrounding Sagittarius A star. It showed a glowing ring of plasma encircling a shadow, a place where light itself could not escape. The black hole did not emit light, but its presence distorted the paths of photons, revealing its shape in silhouette. It was not just a theory anymore. It had a face. And that face stared back into the heart of our own galaxy. A quasar is not a star, nor a galaxy, nor any kind of structure we can see with the naked eye. It is a process, a phenomenon driven by the most extreme environment in the known universe. The area surrounding a supermassive black hole. The black hole itself remains invisible, hidden behind its event horizon. But it is not the black hole that shines. It is the violence around it. Matter falling toward the black hole releases energy. And not just some energy, more than any fusion reaction in a star, more than any supernova. It is the power of gravity, unleashed. As gas and dust spiral toward the black hole, they do not fall in all at once. Instead, they form a disk, a thin, hot, rotating structure called an accretion disk. The particles in this disk crash into each other at incredible speeds, converting gravitational potential energy into heat and light. The temperature soars to millions of degrees. Friction, turbulence, and magnetic fields tear through the disk, making it glow across the entire electromagnetic spectrum, from radio to X-rays. This is the heart of the quasar, the engine that never rests. But the process is far from smooth. The flow of matter is turbulent and unstable. As the gas heats up, it emits intense radiation. That radiation pushes back against the inflowing material, creating a balance, a feedback loop. When the radiation becomes too strong, it blows the gas away, cooling the disk and dimming the light. But then, gravity pulls the gas back in, reigniting the process. This pulsating rhythm can last for millions of years, keeping the quasar bright and violent over astronomical timescales. The energy released in this accretion process is staggering. Even a small amount of matter falling from a safe orbit down to the edge of the event horizon can release a significant fraction of its rest mass as radiation. Compared to nuclear fusion inside stars, which converts only a small percentage of mass to energy, accretion is vastly more efficient. It is one of the most effective engines nature has ever produced, and it needs no fuel but gravity and chaos. But the process is far from smooth. The flow of matter is turbulent and unstable. As the gas heats up, it emits intense radiation. That radiation pushes back against the inflowing material, creating a balance, a feedback loop. When the radiation becomes too strong, it blows the gas away, cooling the disk and dimming the light. But then, gravity pulls the gas back in, reigniting the process. This pulsating rhythm can last for millions of years, keeping the quasar bright and violent over astronomical timescales. These jets are not random. They are narrow, focused beams of radiation and particles shooting out from the poles of the black hole's spin axis. Some stretch for hundreds of thousands of light years, piercing through galaxies and into intergalactic space. The magnetic fields, anchored in the disk and twisted by the rotation of space-time itself, act like giant particle accelerators. They channel the chaos into coherent force. These jets produce the radio signals we detect from Earth, the original whispers that led us to discover quasars. What is most astonishing is that all of this, the light, the heat, the radiation, the jets, comes from matter that never even touches the black hole. Most of the gas in the disk is eventually consumed, but the energy is released long before that. The real drama happens just outside the event horizon, where gravity, motion, and magnetism conspire to extract as much energy as possible from infalling matter. The black hole feeds, but it also blazes, announcing its hunger across the cosmos. This makes quasars unique. They are not objects, they are events. They are not permanent structures, they are temporary storms. The moment the black hole runs out of food, the light fades, the jets stop, and the galaxy returns to silence. But as long as there is something to consume, gas clouds, stars, or unlucky planetary systems, the engine roars. Quasars are the most powerful sustained energy sources in the universe. They are fueled by gravity, shaped by magnetic fields, and constrained only by the boundaries of physics itself. At the edge of a supermassive black hole, something extraordinary happens. As matter spirals inward, the intense gravitational field twists space and time into a swirling funnel. The gas does not fall straight in. It rotates, accelerates, and heats. Magnetic fields, once weak and tangled, become stretched and amplified by the rotation of the accretion disk. This dynamic environment, chaotic and unstable, creates the conditions necessary for one of the most astonishing phenomena in the universe, the launch of relativistic jets. These jets are not like solar flares or stellar winds. They are focused, narrow beams of charged particles and radiation that erupt from the poles of the black hole, shooting outward at nearly the speed of light. The jets are not expelled from within the black hole itself. They arise just outside the event horizon, where matter and energy still obey the rules of physics. In this liminal zone, magnetic fields become engines, converting rotational energy into forward thrust, flinging particles across interstellar space. One of the key mechanisms believed to power these jets is known as the Blandford-Znajek process. According to this model, a spinning black hole drags the fabric of space-time around it, twisting magnetic field lines anchored in the surrounding accretion disk. These field lines act like giant coiled springs, storing energy. When they snap open, they accelerate particles along their axis, away from the disk and out into space. The result is a twin jet structure, one streaming above the disk, the other below. The structure of these jets is breathtaking. Some stretch for hundreds of thousands of light years, punching through entire galaxies and beyond. Within the jet, the matter is so highly energized that it emits across the electromagnetic spectrum, radio waves, X-rays, and gamma rays. And yet, despite their violence, these jets remain astonishingly focused. They do not scatter or dissipate immediately. Instead, they carve channels through space, transferring energy from the galactic core to the intergalactic medium. Magnetic fields are the silent architects of these structures. In everyday life, we rarely see their true potential, but around black holes, they become dominant forces. Charged particles in the accretion disk spiral along magnetic field lines, creating powerful electric currents. These currents twist and amplify the fields themselves, building a feedback loop that stores immense amounts of energy. When the conditions are right, the field lines open outward, allowing matter to escape along their trajectory in the form of a jet. As the jet moves through space, it remains collimated, meaning it does not fan out like a flashlight beam. This is due to the combination of the black hole's rotation, the strength of the magnetic fields, and the pressure from the surrounding interstellar medium. The fastest particles within the jet move at speeds close to the cosmic speed limit. They slam into ambient gas and dust, heating the surroundings and creating bright shock fronts visible from Earth. In some cases, they form vast radio lobes, bubbles of plasma that shine for millions of years. We see the evidence of these jets in every direction. Some appear as long streaks in radio images. Others are visible in X-rays, emerging from the cores of elliptical galaxies. In the most extreme cases, if a jet is aimed directly at Earth, it appears even brighter, magnified by relativistic beaming. These objects are known as Blazars, hyperactive quasars that outshine entire galaxies. The orientation of the jet changes how we perceive the object, but the engine behind it remains the same. A spinning black hole wrapped in a magnetic storm. It is tempting to think of black holes as silent, passive consumers, cosmic drains into which all matter falls. But in truth, They can be among the most luminous objects in the universe. They feed, yes, but in doing so, they rage. The jets they produce are not side effects. They are signatures. They tell us where the energy goes and how the black hole affects everything around it. From the smallest electrons to the largest galaxy clusters, the influence of these jets is both immediate and long-lasting. And yet, for all their brilliance, we still do not fully understand how these jets are formed. Observations confirm their presence, models reproduce their behavior, but the exact moment, the precise physics that channels chaos into symmetry, remains a mystery. What we do know is this: when the conditions are right, when magnetic fields twist tightly enough and matter churns hot and fast enough, nature builds something terrifying. A cosmic lighthouse, shining through the dark, powered by gravity and magnetism alone. When we look out into space, we are also looking back in time. Light takes time to travel, and the farther we peer, the older the image becomes. Through this lens, quasars tell a remarkable story. They are not evenly spread across the universe. Instead, they cluster in the past, crowding the early epochs of cosmic history. The farther we search, the more quasars we find, their light echoing from a time when the universe was still young, chaotic, and forming its first great structures. The most distant known quasars come from an age when the universe was less than 1/10 of its current age. Some ignited just a few 100 million years after the Big Bang, blazing forth before most galaxies had fully formed. They served as beacons in the cosmic dawn, lighting up the darkness and marking the locations of supermassive black holes that had already grown to unimaginable size. But how could these monsters exist so early? Their presence challenged every theory of black hole formation. In today's universe, quasars are rare. Most galaxies, including our own, have quiet cores. Their black holes still exist, but they are no longer actively feeding. Without a steady stream of matter, the engine stalls and the jets disappear. This suggests that quasars are a phase, a temporary but transformative period in the life of a galaxy. During this time, material rushes into the galactic core, fueling the black hole, igniting the quasar, and unleashing radiation that can affect the entire galaxy and beyond. The feeding process of black holes also presents a paradox. There is a limit, known as the Eddington limit, beyond which radiation pressure pushes matter away faster than gravity can pull it in. This limit should cap the rate at which black holes grow. Yet, some early quasars seem to have bypassed this constraint, feeding more rapidly than theory allows. Were these black holes shielded somehow? Was their environment so dense and chaotic that normal rules broke down? The physics of extreme accretion remains one of the great frontiers in astrophysics. And yet, the imprint of that era remains. The radiation from ancient quasars shaped the intergalactic medium, ionizing vast regions of space and influencing the evolution of galaxies. The black holes that powered those distant quasars still sit in the centers of galaxies, including our own. They are sleeping giants, waiting for the right conditions to rise again. Quasars may be echoes from the past, but they are also warnings from the future. The universe remembers. It records its most violent moments in light and sends that light to us across billions of years. For all we have learned about quasars, much remains cloaked in mystery. They are the brightest sustained sources of energy in the known universe, yet their origins still challenge our understanding of physics and cosmic evolution. The most unsettling question lies in time itself. How did quasars appear so early? Some of the most distant quasars began shining when the universe was less than 1 billion years old. That is barely enough time for the first stars to be born and die, let alone build supermassive black holes with billions of solar masses. By the models we know, black holes form from the collapse of massive stars. These stellar remnants then grow by consuming gas or merging with other black holes. But this process takes time, much more time than the early universe seemed to offer. For the earliest quasars to exist, their black holes must have grown at impossible speeds or formed through unknown processes. Some scientists propose that massive clouds of gas collapse directly into black holes, skipping the phase of star formation altogether. But these remain hypotheses, bold, elegant, and still unproven. And yet, the imprint of that era remains. The radiation from ancient quasars shaped the intergalactic medium, ionizing vast regions of space and influencing the evolution of galaxies. The black holes that powered those distant quasars still sit in the centers of galaxies, including our own. They are sleeping giants, waiting for the right conditions to rise again. Quasars may be echoes from the past, but they are also warnings from the future. The universe remembers. It records its most violent moments in light and sends that light to us across billions of years. The feeding process of black holes also presents a paradox. There is a limit, known as the Eddington limit, beyond which radiation pressure pushes matter away faster than gravity can pull it in. This limit should cap the rate at which black holes grow. Yet, some early quasars seem to have bypassed this constraint, feeding more rapidly than theory allows. Were these black holes shielded somehow? Was their environment so dense and chaotic that normal rules broke down? The physics of extreme accretion remains one of the great frontiers in astrophysics. Even the jets that define many quasars pose questions. We understand the magnetic structures that produce them in broad terms, but the precise mechanism, the moment when energy becomes motion, is still unclear. Why do some quasars produce massive, well-formed jets, while others do not? Why are some radio loud and others silent? Is it orientation, black hole spin, or something else entirely? The universe gives us clues, but not yet a full explanation. It is as if we are listening to a song we have only partly learned to hear. In the end, quasars show us who we are in the grand scale of time. We live in the calm after the storm, walking beneath skies once ignited by cosmic flame. But their echoes remain, etched into the space around us, stitched into the very structure of the galaxies we call home. They are not distant, they are within us. They remind us that the universe has a history, that light travels, and that every journey, no matter how bright, begins in darkness. And perhaps, in understanding quasars, we take one step closer to understanding ourselves. Faced with contradictions in time, mass, and structure, scientists have begun to explore new hypotheses. Some of these ideas challenge long-standing assumptions about how black holes form and how galaxies evolve. One possibility suggests that in the early universe, clouds of gas did not need to form stars before collapsing. Under the right conditions, if the gas was dense enough, hot enough, and free from heavy elements, it could have skipped the stellar phase entirely, collapsing directly into massive black holes. Another bold idea points to dark matter, the invisible substance that makes up most of the matter in the universe. In standard models, dark matter does not clump on small scales, but some versions of the theory suggest that dark matter could interact slightly with itself. These interactions might allow dense regions of dark matter to collapse under their own gravity, forming black holes even before the first stars were born. These so-called primordial black holes could have served as seeds for the earliest quasars, lighting up the cosmos before any galaxy had matured. There is also a growing belief that the physics of the early universe was more extreme, more violent, and perhaps more efficient than we previously thought. Star formation may have followed different rules when heavy elements were rare. In this environment, stars could have grown to enormous sizes, hundreds of times more massive than the Sun. When they collapsed, they would have left behind black holes already large enough to skip the slow process of accretion and immediately begin the work of becoming quasars. None of these hypotheses has been proven, but they represent our best efforts to bridge the gap between observation and theory. Each offers a different path to the same destination, a universe that formed black holes faster, earlier, and more violently than our current models allow. As telescopes grow more powerful and simulations become more precise, these ideas will be tested. Until then, they remain as possibilities, open doors in our ongoing quest to understand how something so massive, so bright, and so old could appear so soon after the beginning of time. For many years, black holes were seen as isolated phenomena, cosmic oddities hidden deep within galaxies, influencing only their immediate surroundings. But as our observations deepened, a startling pattern emerged. Almost every galaxy, large or small, appears to contain a supermassive black hole at its center. And more than that, the properties of those black holes seem to be linked to the galaxies themselves. This was not coincidence. It suggested an intimate relationship, a co-evolution woven into the very fabric of cosmic structure. Astronomers discovered that the mass of a supermassive black hole is closely correlated with the velocity of stars in the central regions of its galaxy. The bigger the black hole, the faster those stars move. This tight connection implies feedback, a conversation between the galaxy and its core. As galaxies grow by gathering gas, dust, and stars through mergers and gravitational attraction, they also feed their central black holes. In turn, those black holes shape the galaxies that nurture them, releasing energy that heats and redistributes the surrounding material. When a black hole becomes active, the resulting quasar can influence star formation across the entire galaxy. The intense radiation from the accretion disk and the jets of particles launched from the poles flood the interstellar medium with energy. This heats the gas, making it more difficult for it to cool and collapse into new stars. In effect, the quasar acts as a brake, slowing down the rate at which stars are born. This feedback prevents the galaxy from exhausting its supply of raw material too quickly, allowing it to evolve over billions of years. This process explains why some galaxies are bursting with newborn stars, while others are quiet and red, their star-forming days long behind them. A single outburst from a quasar can sterilize a galaxy for millions of years, but that same outburst may be necessary to preserve balance, to prevent a galaxy from burning through its resources in a single cosmic flare. Galaxies and their black holes are not separate entities. They are locked in a dynamic cycle of cause and effect, growth and regulation. Our own galaxy bears the marks of this relationship. Sagittarius A star, the supermassive black hole at the center of the Milky Way, is quiet now, but it may not always have been. Observations have revealed massive bubbles of gamma radiation stretching above and below the galactic plane, remnants of a possible feeding event that occurred millions of years ago. If so, our galaxy once hosted its own quasar phase, a brief era of furious energy that helped shape its current form and perhaps even influence the conditions that allowed life to emerge. The story of galaxies is incomplete without black holes. They are not passengers. They are engines, and the galaxies themselves are shaped not just by gravity and collisions, but by the radiation and regulation that black holes provide. This coevolution, this shared history, is one of the great revelations of modern astrophysics. From quiet spirals to blazing quasars, every galaxy is both a cradle and a crucible, holding within it a sleeping force that, when awakened, can change everything. At first glance, the Milky Way appears peaceful. Our home galaxy spins gently through the cosmos, its spiral arms wrapped in quiet light. But deep at its core lies a sleeping giant, a supermassive black hole known as Sagittarius A star. For now, it is silent. It feeds only sparingly, emitting a faint whisper of radio waves. But evidence suggests this was not always the case. Millions of years ago, something stirred. Gas, dust, or perhaps an entire cluster of stars fell inward. And for a brief moment, the heart of our galaxy roared like a quasar. In the year 2010, astronomers using the Fermi Gamma Ray Space Telescope discovered something astonishing: two enormous lobes of high-energy radiation extending above and below the Milky Way's center. These Fermi bubbles span tens of thousands of light-years and glow with the imprint of a massive energy release. Simulations suggest they were formed by a feeding event, a time when Sagittarius A star consumed a vast amount of matter, triggering jets of relativistic particles that carved out those immense structures. This discovery changed how we view our own galaxy. The Milky Way is not simply a passive observer of the quasar era. It was once an active participant, and the conditions that created quasars in the early universe still exist today, just less frequently. If enough material were to fall into the galactic core again, Sagittarius A star could awaken. The quiet center of our galaxy could erupt into light, sending radiation flooding through the interstellar medium and disrupting the delicate balance of star formation. And the future holds even more dramatic possibilities. In about 5 billion years, the Milky Way will collide with its nearest large neighbor, the Andromeda galaxy. Their stars will mostly pass by each other harmlessly, but their black holes will not. They will spiral inward, dancing through clouds of shredded gas and stars, until at last they merge. This cosmic union will trigger an outburst of quasar activity, reigniting the core of the new galaxy and flooding it with energy. The slumbering black holes will become a single, furious engine. We will not be here to see it, but the physics is already written. Our galaxy's story is not yet finished. It carries scars from an active past and holds the potential for a radiant future. Quasars are not just distant beacons from the early universe. They are chapters in the history of galaxies like our own. And one day, long after our time, the stars will dim, the dust will fall inward, and the Milky Way may blaze again, its heart awakened, its silence broken. Quasars are more than brilliant anomalies. They are reminders that the universe is not silent. They speak across space and time, carrying the voice of gravity at its most extreme. Born from collapse and chaos, they shine as cosmic lighthouses, marking not danger, but power. In their glow, we see the birth of galaxies, the fury of black holes, and the unspoken laws that govern the vast machinery of the cosmos. Their light has crossed billions of years to reach us, whispering stories of a younger, fiercer universe. And yet, for all their brilliance, quasars are fleeting. They do not last forever. They rise when galaxies are young, when black holes feed without limit, and then they fade, leaving behind quiet cores and ancient scars. Their light may dim, but their legacy remains. Every galaxy that harbors a supermassive black hole holds the memory of that firestorm. Every quiet sky hides a chapter of radiant fury. To understand quasars is to understand the rhythm of the universe, the rise and fall, the burst and silence, the storm and the stillness. In the end, Quasars show us who we are in the grand scale of time. We live in the calm after the storm, walking beneath skies once ignited by cosmic flame. But their echoes remain, etched into the space around us, stitched into the very structure of the galaxies we call home. They are not distant, they are within us. They remind us that the universe has a history, that light travels, and that every journey, no matter how bright, begins in darkness. And perhaps, in understanding quasars, we take one step closer to understanding ourselves. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.